Hello and welcome. ALON SELA is here and I'm very happy that you joined me. Today we're going to talk about the Radon-Nikodym derivative. So let's get started. So I've written down here the steps that we are going to go through in order to understand what is actually the Radon-Nikodym derivative. And as you will see, I claim that you already know the Radon-Nikodym derivative, you just didn't know that you know it. So let's see why it's so. And to do this, I'm hoping that you are familiar with the triple omega f P, which is a probability space, and that you all and that also that you are familiar with the PDF probability density function. So let's talk about a measurable. Let's talk about the first step. So in order to understand the Radon-Nikodym derivative, we need to talk about a measurable space. So let's talk about the measurable space omega f. Now suppose that we put two different measures on this space. So the first measure we're going to put on this measurable space is mu, and the second one will be nu, which looks like a V. So these are two different measures on the same measurable space. Now we need to get a grip of the concept of absolutely continuous. So I mean absolutely continuity. So let's say that the measure nu is absolutely continuous with respect to the measure mu. Let's understand what does it mean. So it means that if we have some set from the sigma algebra which mu give it let's call this set A. If mu, the measure mu, give this set A a measure of 0, then we want the measure mu, nu, to give it also a measure 0. So basically, for every set in the sigma algebra F, which the measure mu giving it the measure 0, we want the measure nu to give it also a measure 0. If that happens, we are saying that the measure nu is absolutely continuous with respect to the measure mu. If such thing happens, maybe later I'll give a small example, but if such thing happens, according to the Radon-Nikodym theorem, there is a non-negative measurable function f, which goes from omega to the semi-open, semi-closed, semi-open interval 0 infinity, such that for every set A which belongs to the sigma algebra, we can calculate the measure which nu give this set by the integral over the set of this function d mu. So this thing is by the Radon-Nikodym theorem. Radon-Nikodym theorem. Okay, so let's just repeat it. Let's repeat it. So we said that we have a measurable space, and we have two different measures on it. We have the measure mu and we have the measure nu. We are saying that the measure nu is absolutely continuous with respect to the measure mu if for every set that the measure mu give it a measure of 0, the measure nu also give this set a measure of 0, and it should happen for every let's call it a null set. It should be true for every null set in the sigma algebra. If such a thing happens, then we, according to the Radon-Nikodym theorem, there is a non-negative measurable function f, which takes which go from omega to the semi-closed, semi-open interval 0 infinity, such that we can calculate the measure of the set A given by the new measure by the integral over this set A of the function f d mu. So this is the Radon-Nikodym theorem, and the case which will be most of interest to us will be the case when we are talking about probability which given by the random variable x and by the Lebesgue measure. So we are saying let's apply these two things, but this time not with the mu measure and the nu measure, but with the probability law of given by x and by the Lebesgue measure lambda. So we are saying that if the probability measure given by the random variable x is absolutely continuous with respect to the Lebesgue measure, then according to the Radon-Nikodym theorem there is a non-negative measurable function from R to the semi-open, semi-closed interval 0 infinity, which means that f is greater than 0 or equal 0, such that we can calculate the probability of every set B in the sigma algebra. This time it's the Borel sigma algebra, by the Lebesgue integral. Just let's look at it like this. This time the sample space in this case, the sample space will be R. The sigma algebra will be the Borel sigma algebra, and the probability will be the probability that the random variable x is given by. So In this case, we are saying that if the probability measure P of x, if it's absolutely continuous with respect to the Lebesgue measure, then by the Radon-Nikodym theorem, we have there exists a non-negative and measurable function f from the sample space R to the semi-closed, semi-open interval 0 infinity, such that for every Borel set from the sigma algebra, we can calculate the probability of this set by the Lebesgue integral over this set of the function f d lambda. And just a quick look, here we said that nu is absolutely continuous with respect to mu. Here we are saying that the probability measure given by x is absolutely continuous with respect to the Lebesgue measure. So this is the first step to understand. So according to the Radon-Nikodym theorem, we have this probability which for every Borel set, and we can calculate it using the Lebesgue integral, including this f function, which is a non-negative function, and we can do it because of the Radon-Nikodym theorem. So actually we just spoke about these two parts. Now we are going to make some use, or let's make some use to sets of this form, sets that are semi-open, semi-closed, from minus infinity to x. As I guess you are familiar with the Borel sigma algebra, one can construct the Borel sigma algebra using this semi-open, semi-closed intervals, and when we are doing when we are taking a set like this and asking what the probability of this semi-open, semi-closed set, this is the definition of the CDF, cumulative distribution function, fx of x. So let's write it down. So we know that the CDF fx of x is the probability that the random variable x will take a value in this interval minus infinity to x. This of course should be a closed interval here, and let's now make the connection with the Radon-Nikodym. So if I'm calling, let's also switch colors. So if I'm calling this Borel set B, we can substitute it here, and we get that according to the Radon-Nikodym theorem, we can calculate this probability of this set minus infinity to x by the Lebesgue integral over this set. So by the Lebesgue integral over this set with some function f d lambda. So this is by the Radon-Nikodym theorem, And now I hope you are a little bit familiar with the Lebesgue integral. If the Riemann integral exists, then the Lebesgue integral also must exist. So suppose for a moment that they should be equal to one another. So if I have this Lebesgue integral from minus infinity to x, here open, here close, f d lambda, if the Riemann integral exists, then it should be equal to this Lebesgue integral, and on the same set from minus infinity to x of f, at this time instead of dx, let's use du. So as you can see, we started here, and actually we got to this result. So we got to this result, the cumulative distribution function, the CDF of x, is given by this integral from minus infinity to x over f over the function f d mu, and this is something I guess you are already familiar with. This is how we are calculating the cumulative distribution function, the CDF of the random variable x, and actually now this is why I claimed that you already know the Radon-Nikodym derivative, you just didn't know it. This f is what we are calling a probability density function. So actually the probability density function is this this function here, and this is what we are calling the Radon-Nikodym derivative, and the Radon-Nikodym derivative is also given the symbol d nu to d mu. So this function f is the Radon-Nikodym derivative, and it's actually, when you are going to the when we are talking about a probability theory or a probability space, the PDF, the probability density function, is what is called the Radon-Nikodym derivative. So for example, if we're talking about standard normal random variable, so let's suppose, for example, that x is a random variable which is a standard normal, which means 0 and standard deviation of 1, and the PDF is given by 1 over the square root of 2 pi e to the minus 1/2 x squared. This thing is the Radon-Nikodym derivative of the standard normal random variable. Why? Because we can write the CDF, the cumulative distribution function of x, as the integral from minus infinity to, let's substitute to x by f dx. And now we know that this f is 1 over the square root of 2 pi times e to the minus 1/2 x squared dx. So if I would give it to you like this from the beginning, this thing you already know. You know that this is the cumulative distribution function of a random variable which is distributed normally, a standard normal, and this is its PDF. So if we're taking this process backwards, then we can see this function, which is actually a function of x. We can now put it like this. So this function f is the same. This is the function f. If this integral exists, then it must be equivalent to the Lebesgue integral over the same set. And we just saw by the Radon-Nikodym theorem that we can calculate every set from the sigma algebra by this Lebesgue integral using this f function over this set, and the Radon-Nikodym theorem tell us that such functions exist, and this function is the Radon-Nikodym derivative. So this is it for this video. I hope you enjoyed it and that you learned something new. I certainly enjoy doing it. I hope you subscribe to my channel and give it a big like and share it to somebody that you think can benefit from it. Until the next time, I'm ALON SELA. I wish you continue to enjoy the world of probability, and I'll see you at the next video. Bye bye.